Roger has 5 tennis balls. He buys 2 more cans of tennis balls. Each can has 3 tennis balls. How many does he have now? It is a classic elementary school math problem. Feed this exact prompt into a standard large language model, and the result is surprisingly brittle. The model often outputs a final number that is mathematically incorrect and logically disconnected from the premise. To understand the failure, look at the historical baseline of few-shot prompting. We typically give the model examples of questions paired with direct answers, forcing its architecture to map a complex input directly to a final output. This creates an X to Y bottleneck. The model executes a sequential forward pass that demands an immediate answer, leaving no structural room for intermediate logical operations. In 2022, researchers led by Jason Wei introduced chain-of-thought prompting to disrupt this rigid structure. Instead of asking for the answer immediately, the prompt structure changes to X to C to Y. The model is guided to generate an intermediate reasoning trace, the C steps, before it produces the final answer. By writing out, Roger started with 5 balls, 2 cans of 3 is 6, 5 plus 6 is 11, the model distributes the computational load across multiple distinct steps. But there is a strict constraint on this technique. Chain of thought is not a universal prompt engineering trick for any system. It requires a massive parameter count to function. Generating the sequence bypasses the input-output bottleneck by reallocating how the model spends its compute during inference. Let's look at the internal mechanics of a neural network solving that arithmetic word problem. When we demand an immediate final number, we hit a working memory limit. The model has to calculate the entire sequence within its weights in a single pass. Even the largest models lack the architecture to complex sequential logic into a single matrix multiplication step. The structure jams. Chain of thought alters this generation trajectory. By providing few-shot examples that include a reasoning trace, we change what the model predicts next. Large language models are autoregressive. They produce text 1 token at a time. Because of this architecture, generating an intermediate token buys the model an entirely new forward pass. That newly generated token is added back into the context window. The model rereads the preceding context, plus its own logical step, before generating the next piece. Researchers refer to this iterative, looping mechanism as adaptive computation time. Chain of thought physically allocates more compute to harder problems by stretching out the total generation length. A 10-step math problem receives 10 times the forward passes. Compare that to a simple fact retrieval task, like asking for the capital of France. That requires a short generation length and therefore minimal compute. This intermediate token generation turns inference from a rigid, static memory retrieval task into a highly dynamic, scale-dependent computational process. Theoretical mechanics only matter if the empirical data supports them. This graph tracks model performance on the GSM-8K dataset, scaling from 8 to 540 billion parameters. Standard prompting shows a steady, gradual slope. Plotting chain of thought over this reveals a distinct flatline zone. For models under 68 billion parameters, it dips below standard prompting. Applying chain of thought to small local models actively degrades their performance. Smaller models produce intermediate reasoning steps that sound fluent but contain severe logical flaws. This creates a negative cascade known as hallucination amplification. An early logical error in the reasoning trace corrupts the final answer entirely. The data tells a very different story once we cross the 100 billion parameter threshold. At this specific scale, intermediate reasoning abruptly becomes logically coherent. The chain of thought line hits a hockey stick curve, overtaking standard prompting. The empirical peak occurs with the Palm 540 billion parameter model, which executes highly complex multi-step deductions. Prior to this, the state-of-the-art standard for these math benchmarks required heavily fine-tuning GPT-3 and pairing it with an external verifier. By contrast, the Palm 540B model achieved that state-of-the-art performance in a completely frozen, off-the-shelf state, with 0 weight updates. Multi-step reasoning is not a gradually learned skill. It is an emergent property that appears when a model reaches the precise parameter scale needed to maintain logical coherence across generated tokens. Does this scaling phenomenon only apply to mathematical word problems, or does it indicate a broader architecture for complex tasks? Researchers tested 3 distinct domains to prove generalizability: math word problems, common sense reasoning, and symbolic manipulation. As expected, standard X to Y prompting fails across these disparate categories. Injecting the X to C to Y prompt structure triggers the same exponential capability jump in all 3 domains. This domain-agnostic success shows that the model is performing a general-purpose operation rather than retrieving specialized templates for each subject. This shift highlights how massive language models utilize their internal representations. These models possess vast, complex latent reasoning capabilities embedded within their weights. However, those latent capabilities remain entirely dormant and unmeasurable if we constrain the system with direct input-output queries. Moving forward, engineers have to shift how they evaluate what a model can actually do. Benchmarking cannot solely measure the static model weights. It must also account for the structural capacity of the prompt itself. Increasing parameter count is insufficient on its own. Scaling inference compute is equally critical to the final output. When evaluating a large language model's upper limits, the true bottleneck is rarely a lack of internal parameters. It is our failure to grant the model the token space required to compute the answer.